Good evening and welcome to AP Calculus Office Hours, Monday Night Calculus. I am super excited to have you guys here. My name is Curtis Brown. I am going to be your host this evening. I'm joined by Steve Kokoska and Tom Dick. These guys have got some great things planned for us this evening. Steve's got some great problems involving volume. That's our topic this evening. And then Tom's got some great recommendations and some good examples on the TI technology and some great things to explore there. So before we get started, I do want to point out that we have all of the information for this for these Monday Night Calculuses in a blog on our TI website in the bulletin board. You can go ahead and access that there. I'll make sure that that's here in the chat real quick. All of the links for previous problem sets are there, and then as well as this current set of problem set, and then we always post the solutions on the day after or a couple of days after these sessions, so you can pull up those solutions. And just while I have you, I will also just encourage you to continue to use these problem sets with your students, get them using them in your classrooms, going over solutions. And then we would love to have your students join us on these Monday Night Calculus sessions to ask questions and probe these guys' brains a little bit, because these guys have been at it a while and they're geniuses with this stuff. So I would hope to have your students be able to access that. So without further ado, Steve, go ahead and take it away.
Okay, thanks a million, Curtis. Let me see if I can share my screen here. All right, and let me bring this up. And one more click here. There we go. How's that? Okay?
That looks perfect.
All right. Thank you, Curtis and Korea, for arranging all of this. I do want to echo something you said, Curtis. You know, I do think sort of naively maybe, but I think this is a great resource for AP Calculus teachers and students. I want to remind everybody that Tom and I are still deeply involved with AP Calculus, and we would be delighted to take your questions. We really do enjoy helping the AP Calculus community and look forward to your questions. This topic tonight, Curtis, is sort of a new presentation for Tom and I. I know that you'll remember we did volumes of solids with known cross sections as one of the modules, content modules in TI-Nfocus, which I think is another great resource for teachers on the education.ti.com site. But tonight, what we're going to look at, actually, the way that I view this, is an application of that general idea. So we're going to be taking a look at volumes by disks and washers. And before I get started, I just want to remind everyone, you know, I always get this question about, well, do my students need to know volumes by cylindrical shells for the exam? And the answer is no, they don't need to do that. They don't need to know that. Many AP Calculus teachers do teach that idea, that concept, and that's fine. And in fact, some students even solve problems on the exam by using the method of cylindrical shells. Now, there'll be never a problem on that can only be done that way, but some students actually use cylindrical shells, and I just want to remind you that if it's correct mathematics, it certainly receives full credit. So what I'm going to do, Curtis, if it's okay, I'm going to start with just a quick review of this general idea. So here's a definition, and it says, look, let's suppose that we have this solid that lies between x equal a and x equal b. And if we know the cross-sectional area of S in the plane P sub x that's perpendicular to the x-axis, if we know that cross-sectional area is a of x, and a is a continuous function, then this is the formula for the volume. And we actually derive this formula on TI-Nfocus. We go through Riemann sums and everything. One thing that students find a little unsettling sometimes when they look at this formula is they think, well, wait a minute, I don't see a pi in here. Or some students say, look, there's got to be a square root of 3/2 in there. And not necessarily. If you know the cross-sectional area of that solid, then you can find the volume. Oh, so yeah, I'm going to take a quick, closer look at this, and then we'll take a look at disks here. I think of this expression this function a of x as sort of a moving cross-sectional area that's obtained by sort of passing a plane through S that's perpendicular to the x-axis. And there are a wealth of good visual aids out there, and Tom's going to do some great stuff with the Nspire also. So if S is a cylinder, think of a right cylinder, and the cross-sectional area is A, then the volume of that solid is just the area of the base times the height, B minus A. And that sort of agrees with our sort of intuition here. So that's just sort of a quick review of that idea. Let's take a look at this disk method, see if we can apply this idea. So, all right, suppose we have a region in the plane and it's revolved about a line in the plane. The resulting solid is called the solid of revolution, and the line is called an axis of revolution. So here's my region in the plane right here, this blue shaded region. And I want you to notice that this line, this axis of revolution here at C, is a bounding curve to that region. Okay? It is a boundary to that region. So now I'm going to take that region and I'm going to revolve it around that line, y equals c. And this is roughly not a bad picture of the solid that I get over here. So how do I figure out the volume of that solid? Well, I'm going to try to apply this general method that we just talked about on the previous page. So I'm going to look at a cross-section of that solid at an arbitrary point in that region. I'm going to look at a cross-section at x. So you can sort of picture me passing this plane through the solid. And the cross-section in this case would be, well, this disk. The question is, can I figure out the area of that disk? Well, it's just the area of a circle. I know the area of a circle is pi times r squared. And what's the radius? What is this distance right in there? Well, let's see. The distance from here to here would be f of x, and the distance from here to here is c. So if I want that distance, I subtract. And so that's just pi times f of x minus c quantity squared. Now, we usually think of this disk method in a little bit more general terms, so that the volume of the solid, I'm going to look right here at this expression, is pi times the definite integral from a to b of the radius squared. So here's a little bit more formal statement of the disk method, and then we'll get into solving some, I think, some cool problems here. To find the volume of a solid of revolution using this disk method, we use one of the following formulas. So if we're revolving around a horizontal axis of revolution, there's the volume, pi times the definite integral a to b of r of x squared. And this indicates that we want an expression for that radius in terms of x. And if we have a vertical axis of revolution, similarly, there's the formula for the volume. Now, give me just 1 second here, Curtis, before I look at an example or two. I'm going to take a closer look at that formula, because I think there are some stumbling blocks here for some students. So this r of x or r of y represents the radius of a representative or a typical disk. And often we draw those typical disks in to help us. And I'll show you how I attack this in just a minute. This number 2 here is really important to me, and I'm going to connect that with a minute down here at item number 4II. The radius of this disk is always perpendicular to the axis of revolution. And in my mind, that helps me determine actually what the variable of integration is. So in this case, for number 3, using the disk method, the region R always has the axis of revolution as a bounding curve. If the region does not have that axis of revolution as a bounding curve, well, then we need another method. We need some other way to figure out that volume. So what I've done here in number 4 is try to list what I believe are 2 of the most common ways to determine the variable of integration. My experience with this in teaching Curtis suggests that this is one of the biggest obstacles for students in applying the disk method. How the devil do I determine what the variable of integration is going to be, and therefore, how do I determine an expression for the radius? Well, the two most common ways are, I think, first of all, to think about Riemann sums and to draw in sort of a representative rectangle. And if the width is delta x, then we integrate with respect to x. If the width is delta y, then we integrate with respect to y. Now, the way that I do this, and that's fine, but the way that I do this is I try to draw a radius of an arbitrary circular cross-section. And I ask myself, well, if the radius is perpendicular to the x-axis, then I know I have to integrate with respect to x, and I know I need an expression for the radius in terms of x. And similarly, if the radius is perpendicular to the y-axis, I'm going to be integrating with respect to y. And one more note before we do a problem here. If the plane region is bounded by the graph of f in the x-axis, then the radius is f of x. And I'm sorry I didn't include a picture here, but I'm going to draw a quick one. So here's my function up here, y equal f of x. And if my region is right here from A to B, and I'm revolving about the x-axis, then the radius is just at an arbitrary value x. The radius is just that distance up to the curve, and so the radius is just equal to f of x. So that's a pretty common first sort of a problem. So let's try one. So let's think about a region that's bounded by the graph of this parabola, x minus 2 squared, and the x-axis between 0 and 1. And we're going to rotate about the x-axis, and we want to find the volume of the resulting solid. So I started out, I'm going to keep some of my calculations hidden here for a second, and I might even have a question or two coming up. Here's my region R because, well, darn it, there's the parabola. Bounded between 0 and 1. Okay, there's the origin, and there's 0. And I'm going to take this region and I'm going to revolve it around the x-axis. Okay, so the axis of revolution is a bounding curve, so I feel comfortable using the disk method. And now what I'm going to do is I'm going to pick an arbitrary value x in this region between 0 and 1, and I'm going to write a little bit. I actually do this when I solve these problems with my students. If that's my radius, I note that r is perpendicular to the x-axis. And that tells me that, you know what, I'm integrating with respect to x. Now, I won't write this down, but I also write down when I'm teaching to remind myself the axis of revolution is a bounding curve, and therefore I'm going to use the disk method. So, okay, here we go. The volume is equal to pi 0 to 1, a to b, 0 to 1. And this expression right in there, that x minus 2 squared, is the radius, because at an arbitrary value x here, this distance is the distance or the height of the curve, x minus 2 squared, and there's the radius squared. So I did a little bit of simplification, and now the question is, how the devil do you integrate that? Well, one way, of course, is, I guess, I could multiply that all out and get a fourth degree polynomial, and that's fine. But I guess maybe a simpler way to do this would be to recognize that, you know what, I really can use, oops, I'm sorry, a u substitution here with u equal to x minus 2. So this is what I would call in my class, Curtis, almost integration by inspection. It's a pretty simple u substitution. And I'm going to do it without any transforming of variables. So I get a u to the 5th over 5, or an x minus 2 to the 5th over 5, and I plugged in the bounds. And I think I got a 31 pi over 5, which is pretty cool. That's a nice problem.
Yeah.
Nice one to start out with.
That is a good one to start with.
So here's one, I think, where we might need technology. Let's consider the region bounded by the graph of y equal e to the minus x squared, the x-axis between 0 and 2. And once again, we're going to revolve this about the x-axis. There's my region R. I'm going to take this about the x-axis. And sorry, I'm going to write a little bit more up here for my own benefit. R, once again, is perpendicular to the x-axis. I'll draw it in again in a minute. So that means I need to integrate with respect to x. Here's an arbitrary value in the region between 0 and 2. There's my radius r. I can see that it's simply the height of the curve at that value x. So I think I'm ready to go. The volume is pi times the integral from 0 to 2 e to the minus x squared. I'm going to do just a little simplification here, and I get an e to the minus 2x squared. And try as we might, Curtis, we cannot integrate that. This is a classic problem in which we would need technology. And I think I went up here to the TI-Nspire and did that and got a 1.969. And I'm going to add in a little bit more here. If you were doing this on the AP exam, you could also respond with a 1.968. So we'll take it rounded or truncated. So that's a nice one too. And while I'm here, Curtis, just for the heck of it, where does that expression, whoops, I'm sorry, where does that expression that e to the minus x squared occur frequently in probability and statistics? I know we have a lot of people who also teach AP stats. You know where that occurs frequently?
Well, I can make a guess.
Shoot, go ahead. I'll take it.
I mean, what you've got there sure looks an awful lot like a bell curve of some sort.
Sure, very good. I mean, part of the normal curve.
I'm gonna be careful to say normal because that's a very specific curve, but
very
at
good.
least a bell-shaped curve.
Yep, some constants in there, and you would get a bell-shaped curve. Very good. A valid normal probability distribution. Very good. Very good, Curtis. Let's try another one. So the region bounded by y equal x squared, y equal 4, and x equals 0 is rotated about the line y equal 4. Here's my line, y equal 4. Here's my region R. So this time I'm not going about the x-axis, but I'm going to take this region R and I'm going to rotate about that line y equal 4. Well, maybe I'm jumping the gun a little bit here, but I do see that the axis of revolution is a bounding curve, so this would be good for a disk method. I'm going to pick an arbitrary value of x in the region. I'm going to draw in a radius, and I'm going to write a little bit off to the side here and then see if I can figure out an expression for that radius. That R is indeed perpendicular to the x-axis, so that's a signal that I'm going to be integrating with respect to x. And again, the axis of revolution is a bounding curve. Let's see, can we get an expression for that radius? Well, let's see. It's 4 all the way up to here. And I know the distance from here to here is what, x squared. So that radius is equal to 4 minus x squared. I can see that. So let's see, the volume would be 0 to 2, an integral from 0 to 2, the radius squared. And for this one, I'm going to have to multiply it out. Maybe there's an easier way, but I'm going to have to multiply this one out. Curtis, do you see why on this one? By any chance, why this isn't a nice, easy U substitution?
Yeah, it looks like you've got an extra term there that's not going to work out very well.
Yeah, I don't have that derivative of the inner function hanging around. Very good. It's part of the integrand. Very good. Very good. So, all right, I multiplied out. I got a 4th degree polynomial. The integration is pretty straightforward. A couple of applications of the power rule. I plugged in my upper bound. I plug in the lower bound, 0, I get 0. And as my college professor used to say, as anyone can plainly see, that works out to be 256 pi over 12. And I think there's a little simplification in there too. I'm sorry that I didn't do it. I think it's 64 over 3 pi. How about that? Okay.
Yeah. Yeah, I think that works out nicely.
Cool. All right. So what happens if the axis of revolution is not a bounding curve? So what we do is we express the volume as the difference of 2 volumes. So here's my setup and here's my picture, and I'll do my best to explain this one. So let's see, here's my region in here, this blue colored region. And what I'm going to try to do is to take that region and revolve it about the line y equals c. And the way that I've drawn this is that R is bounded by the graph of f and g and the lines x equal a and x equal b, not the line y equals c. So I'm going to take that region, revolve it about y equals c, and I get something that looks like this over here on the right-hand side. And there's a cross section. And if you take a look at this cross section over here in green, it kind of looks like a washer that you'd put into your hose. Okay, it looks like a washer. So what's the area of that washer? Well, we take the area of the outer circle and we subtract off the area of the inner circle. So it's just pi times the outer radius squared minus pi times the inner radius squared. And here's a way that I often remember that formula. And here it is. Here's the volume of that solid in a way that we might remember that formula. I'm going to write something here, Curtis. I know this is a bad thing to do, but I'm going to write something that's wrong up here, but I will at least put some not equal signs in here. One of the most common errors we see on the AP Calculus exam is, and related to these types of problems, is something like this, where students take the difference and square it. And those two things are definitely not equal. And I remember sometimes this is called a freshman's dream, to think that those two are equal, but they're not. That's a common error.
Yes, for sure.
So let's try one. The region bounded by the graphs of y equal 2 minus x squared, y equal x squared 0 revolved about the line y equal 3. Holy Toledo, find the volume of the resulting solid. All right. So let's see, here's y equal x squared, here's 2 minus x squared. One of the first things I did was find the point of intersection of those two graphs. I did that over here to save a little bit of time. These graphs actually intersect where x is equal to -1 and +1, but I'm only interested over here in the first quadrant. So this is the point, I believe, 1, 1. So I want to take this region R and I'm going to revolve it about the line y equal 3. That is not a bounding curve, so I have to use the washer method. So let me add a couple of labels in here. This is my outer radius. That's my inner radius, and I need expressions for both of them. And by the way, both of those radii are perpendicular to the x-axis, so I know I'm going to be doing this with respect to x. So let's see if I've got this right. The outer radius is 3 minus that little bitty distance in there, which is x squared. The inner radius is 3 minus this distance. Let's see, that's 2 minus x squared, and I did a little bit of simplification. So now I've got the outer radius, I've got the inner radius. I'm going to do my best here, Curtis, to put that together on the next page. So let's see, this is the outer radius squared minus the inner radius squared. Now, I think this is a common error here too. One thing that you can certainly do at this point is you can simplify the integrand as much as possible. And I think that's a step that's often lost on some of our students. So what I did is I expanded out both of those binomials and I simplified a little bit, and I got this pretty simple quadratic. I factored out an 8. I used the power rule a couple of times, and I think I got a 16 pi divided by 3. Very cool problem.
Yeah, that is a good problem.
Now, we don't do too much here, Curtis, or we haven't done much with our BC students and teachers. I'm just going to add a challenge over here for our BC teachers and students. This is a problem that I think that they should do related to this and related to something that we've done in the past. So here's what I'm going to consider. I'm going to take a look at the graph of y equal 1 divided by x, and I'm going to consider the region from 1 all the way out to infinity. So that's my region R. And one of the first things I'm going to ask the BC group to do here is to find the area of that region. I'm going to write it like that, area of R, and I'm even going to help you a little bit. That would be the integral from 1 to infinity of 1 divided by x dx. Now that's an improper integral, and we haven't done much of this with our BC group, but I encourage you to find an answer to that. So I'll leave that as an open question. It seems like a pretty obvious answer because I've got an infinite region The way that I talk about this in classes, I need an infinite amount of fence to fence in that region. Well, shoot, the area has got to be infinite, but you need to find this answer. You need to solve this. And now what I'm going to do is I'm going to take this region and I'm going to revolve it about the x-axis. So now what I want you to do is to find the volume of R, and I'll just leave that as an open question. And you should compare these two answers because they just don't seem right, but they are. Very, very cool.
Yeah, that is a really interesting one for sure.
All right, I'm going to switch just a little bit here, Curtis, and I'm going to take a look at a couple of the solutions from the exercises that we assigned. I'll run through a couple of these kind of quickly, and then I'm going to hand it over to Tom, okay?
All right.
So the first problem we asked about is, let's suppose R is the region in the first quadrant bounded by the graph of this expression, this function, the coordinate axes and the line x equal 1, and we want to find the volume obtained, the volume of the solid obtained when R is rotated about the x-axis. So let me see here. I'm going to skip around a little bit, but here's my figure down here. This is a graph of 4 divided by that square root, 1 plus x squared. So there's my region R between 0 and 1. And I want to take that region and I want to revolve it about the x-axis. So thinking out loud here, I'm going to draw in a radius, a typical radius at x. And I note that R is perpendicular to the x-axis. That's a good thing. So that means I'm going to be integrating with respect to x. I also note that the axis of revolution happens to be a bounding curve here. So this is a classic example for the disk method. And so let's see, the radius is actually pretty easy here. This is one of our typical examples where we're taking this region revolving about the x-axis. So the radius is simply the value of this function at an arbitrary point or value x. So here we go. The volume is pi times the integral 0 to 1. I'm a little worried about that square root in the denominator. But when I square everything, don't let me make a mistake here. I think the 16 comes out front. There's the 16 pi. And now I've got 0 to 1, 1 divided by x squared. One of the first things I think about, Curtis, when I see that integrand is, well, I'd like to try a u substitution, but I don't have the derivative of the denominator as part of the integrand,
right,
as part of a product. And then I remember, oh, wait a minute, that's just the derivative of the inverse tangent. So this is actually an integration by inspection. I often get this question, do my students need to know that one by heart? And I would say, yes, they need to know that one. They need to recognize that. So that's the inverse tangent of x.
Yeah, that's one of those that we used to refer as you got to know it cold.
You do indeed. I agree, Curtis. You got to know this one cold. So I plug in the upper bound, I plug in the lower bound. Let's see, the arc tangent or the inverse tangent of 1 is pi over 4. And the inverse tangent of 0 is 0. And so I think this works out to be exactly 4 pi squared. And that's pretty cool. I'm always amazed at this, that the exact volume of that solid is 4 pi squared.
That is kind of cool.
It is neat. And I've done a little bit here, the best that I could on the right-hand side here. This is a picture, I think, of what this solid might look like. Sometimes I can get a little fancy here and actually draw in this curve. I didn't do that here, but there it is. It's on top there. And I went from 0 to 1. It's kind of hard to see, but I do have that x value of 1 in there. And let's see, there's the y value of 4. And you can kind of see this solid revolving about the x-axis sort of coming out at you, coming out of the page. It's kind of a neat one.
Yeah, that's a nice picture.
All right, let's try one more here. See if we can do this one. This was kind of a neat problem. I credit Tom with thinking about this one. This is very cool. So let R be the region in the first quadrant bounded by the graph of 36 minus x squared in the coordinate axes. Here's my region R. And it says a container has the shape of the solid formed by rotating R about the x-axis. Okay, so I'm going to take that and rotate it about the x-axis. And here we go again. I'm going to draw in an arbitrary radius R at x. So let's see, R is perpendicular once again to the x-axis. So that tells me I need to integrate with respect to x. That tells me I need to find an expression for the radius in terms of x. And again, this is an easy one when we have this kind of a region. So R is just 36 minus x squared. I'm going to do the calculations on the next page, but here's a figure of what this, a picture of what this solid of revolution would look like. That's pretty cool. And let's see if we can do this one. Holy Toledo. So the volume is pi times the integral from 0 to 6. There's my radius. Whoops, I'm sorry about that, Curtis. Squared. And again, I don't have the derivative of that inner function as part of the integrand. So I'm going to have to multiply everything out and get a polynomial of degree 4. I have to integrate term by term. Power rule several times. And this one is, wow, 20,736 pi divided by 5. Yikes. And I think one of the questions that Tom asked about in this exercise is how many liters of water is this? And I think it works out to be about 13.029 liters. One question, I'm sorry, go ahead, Kurt.
Oh, I was just going to ask a question. Would I get credit for saying it would hold 0 liters of water? I mean, it's on its side. Everything is pour out.
There's always one in the crowd, you know?
Wouldn't you know it, it's your host.
Well, you know, one question seriously I get is, if you had this on the AP exam, would you have to simplify this expression to that fraction? And the answer is no. Remember that this is a final numerical answer right there, and final numerical answers do not need to be simplified. And in fact, often students make a mistake when simplifying, and so we encourage them not to do that. Not in my class, but on the exam. Let me do one more and I'll hand it over to Tom. So now we're going to take find the volume of another container where we take that same region, but this time we revolve about the y-axis. So I apologize. I'm going to sneak down and look at the picture first. So this time I'm going to take that region. I'm going to revolve about the y-axis. So let's see. This time if I draw in a radius, there it is, R, at an arbitrary point y along the y-axis. So R this time is perpendicular to the y-axis. So that tells me I need to integrate with respect to y. So that tells me I need to find an expression for R, let's see, in terms of y. So the way that we do that is shown on this line. We actually have to turn around and solve for x in terms of y. It's as if y is the independent variable and now x is the dependent variable. So for a given value of y, how far out here along the x direction do we go? So if we solve for x, we get this expression. We take the positive square root, again, because we're going in the positive direction here. So my radius, I'm just going to scribble it in down the bottom here, r of y is the square root of 36 minus y. And again, I'm a little worried about that square root, but let's follow this through and see what happens. So we have pi times the integral. Be careful. How does y vary? 0 to 36 this time of r, the radius squared. And oh boy, this works out pretty nicely. That's a pretty simple integrand. We integrate term by term. Again, 2 applications of the power rule. And that just becomes, I think, 648 pi. That's pretty big. And I don't, yeah, I think that's correct. That's the number of liters of water that this container would hold. And to finish this off, I think here's a picture of this solid. So I take this region, there's my curve. You can almost see it there as one of those lines. And I take that and revolve about the y-axis, and that's the resulting solid. And that's pretty cool. We'll have the other solutions posted with a couple of pictures, I think, also. And I think Curtis Tom's going to show you a couple of nice pictures with the TI-Nspire. So I'm going to do my best to stop sharing.
Well, that sounds perfect.
Pass it over to Tom.
Okay. I will try to share my screen and I'll share desktop and then go into Nspire. I thought I might pick up where Steve left off with the problems that we had, because I think there's some nice points to make that are particularly relevant for AP. And so this was the third problem. And it's lit RB, the region bounded by the graphs of y equals 2 minus x squared and y equals e to the x. And find the volume of the solid generated when r is rotated about the x-axis. So I'm going to go ahead and pull up the solution, I hope. Let's see. There we go. And I've got a split screen here. And to the right, that right pane, if you will, is the graphs of those two functions. Right? F1 of x is 2 minus x squared, and F2 of x is e to the x. And this was one of those situations where our bounding curves are not along one of the bounding curves. Excuse me. Our two graphs are the bounding curves, neither one of which is the x-axis, which we're rotating around. So this is going to be one of those that will result in cross sections that are washers.
Right.
But the point I wanted to make here that was, I think, particularly relevant for AP is this is an example where we're not going to be able to find the intersection points of these two curves algebraically or analytically. But we really are going to need technology. And this is one of those 4 calculator functionalities that students are expected to have access to as a solver. And so you can see I've actually used the solver here. And this is I'm getting numerical solutions. And so this is not needing casts here, actually getting these 2 numerical solutions. And the point that I wanted to make here is my 2 solutions here are negative 1.31597 rounded to, it looks like 5 decimal places. And the other one, it's being reported out to 6 decimal places. If you're wondering about that little exclamation mark in the warning sign, let me click on that, see what it says. It says more solutions may exist. So I could, put some bounds on this. I'm going to leave it as kind of a challenge question to just reason why these are exactly the only 2 solutions to this this equation. So if you think about the calculus of these 2 curves, why will they never cross again? Okay, so we really do have the only 2 intersection points. And I've stored the leftmost intersection point in A and the rightmost intersection point in B. And then we've just set up, as Steve explained, we've got an outer radius is my parabola, the 2 minus x squared. My inner radius is the e to the x. And so I've set up my integral and done, and again, this is a numerically reported result here. So the point I wanted to make here is for reporting purposes, we would report out this integral value, could report it out as 11.113. That would be either rounded or truncated. But the point I wanted to make is I didn't round my A value and my B value here. And that's really tempting to do for students is anytime they come up with a decimal number on an AP exam, they might say, well, okay, 3 decimal places is the key. But my answer to this problem is neither A nor B. I just need those values to set up this integral. And if I prematurely round those off, I'm in danger of getting a integral result that might not be accurate to that third decimal place. So just wanted to put that caution out there. What you're seeing here is really a good way to go when you're using technology on AP exam, is to store those values, like for the intersection points, to as much accuracy as you can as a named constant like A and B here, and then use those as you're setting up. So,
I would just follow that up with, you're virtually guaranteed that if you round it early, that your answer will not be close.
Yeah, it depends.
I mean, it could be close.
Sometimes it's pretty robust, but there's other times students have been caught on that.
Yeah. You're gonna be playing with fire there.
Right.
If you do that intermediate rounding step, it can cause all kinds of big time issues. So I second that.
Tom, I have one other question, and you don't have to do this now, but you've answered this for me probably about 5 or 6 times. But when you use the solve feature or one of the other features of the TI-Nspire, I believe you showed me that there is a way to put the answers into a list so that you can then refer to those answers and use them to the greatest extent, the greatest accuracy that the machine has. So for example, I don't know how you got that value of A, whether you typed that in minus 1.31597, or whether you somehow extracted that from that solve command.
Well, that's one I might defer to Curtis on, but I'll tell you what I did here was I literally just typed them in.
Okay.
So
but I typed them in, to the 5th or 6th decimal place.
Yep. And you're probably pretty good.
Mm-hmm.
You're probably pretty safe, but I know that you've helped me with that. That I don't think it's the solve command. I think it's
There's plenty of ways to extract those, Steve. I think that's a really great question. And maybe if we have enough time at the end, we can do that. Or there's also, we can make the note of that and we'll include it in a future one of these. And make sure that we get that tip in there. But that's a good request. That's a good one.
Okay.
And we do have some comments coming in also about just the number of decimals being a better thing. The better you can do with the decimal, the more exact you can do, the better your answer is going to be as well.
Curtis, may I ask you before Tom moves on, can you also do the same sort of thing on the graph screen? In other words, if you find one of the points of intersection there, can you then store that?
Right.
Yeah.
In fact, it's easier on the graph screen.
Okay.
Mm-hmm. It's easier on the graph screen.
Okay. Thanks, Tom.
Yeah. I'm going to go ahead and go on to problem 4. So this is one of these where we're actually going through, I think, all the problems that we posted. So I'm going to go to the next page here and just take a look at the problem 4 setup. It's actually 2 parts. One of them is kind of an interesting challenge. So first of all, the setup is R is the region bounded by y equals square root of x, the x-axis, and the vertical line x equal 4. And we're going to look at 2 solids. Okay, the first solid, S1, is obtained by rotating that region about the x-axis. And S2, the second solid, is obtained by rotating that same region about a horizontal line y equals 2. Okay, and again, Steve has covered these in his presentation. The question here is, which solid, S1 or S2, turns out to have the greater volume? And show the calculations that support your conclusion. And then part B has the interesting twist, is there another horizontal line different than y equals 2 that you could have rotated the region around so that your solid would have exactly the same volume as the one where you rotated around the line y equals 2. Okay. And this one is asking for both to set up an equation involving integrals that could be used to solve for that constant c, and actually go ahead and use it. Now, on the AP exam, there are often cases where you're just asked to supply that equation involving the integrals and just stop there. But here we're going to go ahead and carry that on out. This was something that really lent itself to some technology use in kind of an interesting way. Part A is really pretty straightforward, especially given what Steve laid out so nicely for us. That volume of S1 is the kind of classic disk method and comes out to be just 8 pi. In fact, the integrand turns out to be really, really nice because I'm squaring the square root of x. And so I just end up integrating x from 0 to 4 and then multiplying by pi to get that final answer. The second one, where we're rotating around the line y equals 2, well, that's going to end up giving us washers. And probably should go ahead and take a look at a picture so we can see really what that region is. So I've got a graph of y equals the square root of x. That's my F1. And we're going from 0 to 4. There's that vertical line, x equals 4. And I've actually graphed the line y equals 2 as another function, just so we could see that. And so we're rotating this region about this horizontal line up here. And that's giving us those washers. And I'll just go back to the actual calculation. We could have just done it numerically, but this is doing it out via the antiderivatives, and we get a final answer of 40 pi over 3. So the answer to part A, just comparing those two values, we have now the exact values of the volumes of both solids. Clearly, the 40 pi over 3 is bigger than the 8 pi. So we can answer that question. Well, let's go to that part B. And what I've done is I've actually plotted a third function here, which is another horizontal line. And this is y equals c. My function's f3 of x equals c. And I've put c on a slider. And I've actually set up the integral for that would give the volume of the solid obtained by rotating that region R about the line y equals c. Okay. Now, it's pretty clear that c is going to have to be negative. That's why I've located it down here. And I'm going through negative values because if c was bigger than 2, we'd have clearly more volume being generated as I move that axis away from the region. And there's some metaphysical problems with actually having a line go through the region. So we won't even go there. So I can actually move that line C up and watch dynamically the value of the integral change up here. And so I've got I think a decimal approximation for 40 pi over 3, so I can compare. And so I can just kind of empirically look for a value of C. It looks like I'm getting close, and oh boy, that looks really nice. It looks like at C equals negative 0.5, this looks really good. Now, you might be convinced enough by looking at those two decimal numbers, but here's the actual solution that we're looking for, where I've actually set up the integral, set it equal to the volume of solid 2, and then solved for C. And sure enough, it comes out to be exactly negative 1/2. Steve, I'm going to pause there to see if you had any comments or.
Yeah, I have one question for you, Tom. When you look at, as you move that slider, and you're getting that dynamic integral, yep, there it is, here it's changing. I think I know the answer to this, but why is that giving me a decimal rather than an exact symbolic answer?
I'm pretty certain it's because the value of C, because it's hooked to a slider, is a decimal.
Okay.
As soon as you have any value within the integral that has a decimal point in it, it kind of reverts to, oh, okay, the answer needs to be numerical.
Yep.
So that begs the question then, is it possible to create a slider so that it slides along symbolic values?
But
let's see, that's a great question. I'm looking at Curtis.
seems like, Steve, what we're asking for here, though, is I mean, as I change that value of C,
Yes.
I'm giving it I mean, just by definition, I'm giving it a value, right? By saying that it's going to be equal to something and I'm going to slide it around. It might be some other number.
Well, here's my dilemma. I see that 40 pi over 3 is 41.8879.
Mm-hmm.
Now, if I come up with a 41.8879 as I slide that C around, I know calculators lie. And I don't know, maybe they differ out in the 6th place.
Sure. Yeah.
So what I'd like to know is it possible that this slider can be symbolic so that when I slide that value of C, I would see answers like 40 pi over 3.
Oh, so you wanted to show an exact set of values. I was sorry. I was thinking symbolic. You were meaning, in terms of the exact cast solution with a plus C or something. So the answer is no. There's not really a way to get that to be returning values of, say, pi over 3 or with pi not multiplied out. Or fractional values in that way. And Tom's reasoning is exactly right, that because we're using a decimal value in that slider, and I can't really define a slider as an exact fraction. If I could use a fraction there, then that decimal point wouldn't necessarily show up, and then perhaps, but the way that it's programmed and written, it will always return a decimal when you're using a slider.
So if you wanted to, could you create a hidden variable that takes C and converts it into a symbolic number and then use that new variable D over there?
You might be able to do that behind the scenes, sure.
Okay.
But I think that would be a lot of work.
So what I was going to say, Steve, is one thing we can do here is we can check. I'm going up to this math box up here. I'm going to actually replace C by a fraction of -1/2.
Okay.
So let's see. In that instance, I'll just put in, editing here, I'll put in -1/2 there. And over here, C shows up twice. I'll put in -1/2.
Curious what you're going to get there.
There. Boom.
That's cool.
So, if you were suspicious at all, say, boy, I think my slider's right on the number.
Yeah.
But because it's in decimal form, I'm not sure. You could say, well, okay, I'll express it in exact form and evaluate it that way. Now, that's not as slick as what you just said, where you might have a slider actually going through symbolic values. But this is a way to confirm I'm actually getting 40 pi over 3 for that value.
Yep.
Right. Yeah.
Very cool. Very cool.
A couple other things, just kind of miscellaneous, I guess, is this is an area where this is a topic where I think students are sometimes struggle to kind of visualize what's going on. And Steve generated some beautiful pictures. I'm not sure what package you use, Steve, to create your graphics of those solids of revolution. But it was clearly something that used a 3D grapher, and maybe it had a built-in solid revolution type of functionality. But if you have any 3D grapher, this is something you can do. And the TI-Nspire has a 3D grapher. So certainly 3D graphing is not part of the AP syllabus. But as a teacher, if you're trying to create some pictures to illustrate solids of revolution. Let me see. Let's go. I'm going to go back to number 1 here. This was the problem where we're rotating 4 over the square root of 1 plus x squared about the x-axis. And we wanted to visualize what that looks like. I just wanted to show you kind of a nice standard technique you can use to create your own. What there will be surfaces of revolution, but then you have the boundary of your solids. So what I'm going to do is go over here to the menu and go to 2 view. Let me go to view. Oh, I messed up here. Let me escape. We'll try that again. So let me go to view. And you'll see that 3D graphing is one of my options here. So let me go to that 3D graphing. And I've actually plotted the surface of revolution that went with problem 1 from our assignment. And here's how it was done. If I go to the menu, 3D graph entry edit, you have 2 choices. They are, you can either plot a function z equals a function of x and y, or a more general one is parametric. And that's what I used here to plot that surface. So I just want to show you basically how that's done. Parametric surfaces, all 3 variables, x, y, and z, are functions of 2 variables, t and u. And notice what I did. I just made x equal to t. And then I made y, my function was already stored in f1. I made y equal to f1 of t times the cosine of u, and z equal to f1 of t times the sine of u.
So, Tom, I want to be really specific real quick because I'm thinking that some people might have missed that, but you've actually got the function already graphed and stored as F1 on your original 2D screen.
Yeah.
And you're using that F1 in this case.
Yeah.
Right.
And I chose to do it this way because now if I go to a different problem and change my function, if I store it in F1, this is already set up to do the volume of revolution or the surface of revolution. On the parameters here, it says edit parameters. My Tmin and Tmax, that's just going to be the boundaries of your region. Like this went from 0 to 1. So that would be your interval that you're integrating over. And your U, to do that full circle, we go from 0 to 2 pi. And
that's
basically
fantastic.
that'll work for, it's a quick way to generate your own. And again, this is not a topic that's within the curriculum. It's more of a tip for teachers. If you have access to a 3D grapher like TI-Nspire has, this is a way you can generate your own.
And that's a really nice thing for students who are struggling with the visualization piece or just trying to even see what they're really going to get whenever they visualize this thing. I think that is really instructive and helpful for students. Tom, we're coming up on time, but I noticed you also had one value,
that was my very last
file from Math Inspired.
Yes, brought this out of Math Inspired. It's Calculus Inspired is just a set of resources that we just want to make sure people are aware of. It has lots of TNS files that help folks visualize or look dynamically at some key topics in calculus. This is one for volumes of revolutions disk method, in which go ahead and you can define a function on a regular calculator page, and then it will automatically graph that function as well as give you a visual of what that solid revolution looks like.
That's really nice.
Change your limits of integration with slider. And you can also move the cross section. That's what that XC is.
That's really nice visualization to be able to see that in action. And I saw on page 1.4, you kind of get see the cross section.
Yeah, it takes that cross
on
section
the left there too,
so you can look at it kind of face on and see that it is a circle. And then it's reporting out the area of that cross section. There is a corresponding file for washers too. So
sure, okay.
Resources there in Calculus-Nspire. And I think that probably takes us to time. So
I think that does take us to time. Thank you, Tom and Steve. I do want to make one more comment, and that is I'm going to post a little link in the chat here. We do have some great resources that Tom and Steve have pulled together for us based on previous free response questions. I know we're coming up on the time of the year where you want to start rehearsing and getting ready for that. It's called TI in Focus. I put the link here in the chat, and I would highly encourage you to go and check out those video resources. And we'll be highlighting those some more as we get closer to the exam in the upcoming weeks. So again, I just want to thank you for this evening. Thank you guys very much, and we'll sign off with that. Good night.